Okay, thank you so much for inviting us, EUROfusion, to this very important and interesting event. I'm Duarte Borba, and I work for EUROfusion. And today I will highlight a number of things that have been already said. So I will, here's my outline. Obviously, as I said, some of the things are already being discussed. I will give a different perspective on some of the elements that already been mentioned, and I will focus in some of the aspects that we do in EUROfusion regarding the development of fusion energy. So I will address nuclear fusion, why, and how, and the impact of nuclear fusion. Regarding why, obviously, the world energy sources is a key aspect where fusion can contribute. I'll discuss a bit fusion versus fission, the advantages of fusion, and how I will describe the technology that is being pursued by EUROfusion, which is a magnetic confinement of fusion plasmas, and the worldwide collaborative effort that EUROfusion is part of. And then impact. I will focus mostly on the activities that EUROfusion is doing in terms of technology transfer. What are we doing to bring the benefits of fusion research and the new technologies to have as quick as possible application to developing and modernizing society through applications directly to industry outside the fusion field. This has already been discussed, and obviously one of the most important challenges that mankind faces is the decarbonization of the energy production. We still use today most of our energy from burning fossil fuels. If we want to have an environmental responsible way of producing our energy and to fight climate change and the aspects related to the pollution of not only carbon dioxide, but all the other emissions that come from burning fossil fuels, we need alternative sources of energy. So this is basically the main, let's say, drive to research nuclear fusion and as an energy source. This is already known, but I give you a little bit different perspective. The way the nuclei in the atom are packed are done in a very peculiar way. It's a combination of electromagnetic repulsion and very strong nuclear forces at play. It means that as you pack more protons and neutrons, the binding energy kind of increases. So you can, if you cannot pack too many protons because of electromagnetic repulsion, but you cannot pack too many neutrons because there's a beta decay that tend to convert neutrons into protons. So there's a balance between neutrons and protons, and this kind of is an energetic advantage to pack as many neutrons and protons until a given point where the nuclear forces, which are very short ranged, start being not so effective, and then there's an inversion, and then it becomes less and less energy efficient to pack more protons and neutrons. And then at some point, the atoms tend to release alpha particles or alpha decay, and then the limit is basically uranium as the last fully stable element. So basically, nature has offered two possibilities. You can release energy by fission, by breaking down mostly uranium, or fusion by combining very light elements like hydrogen or the heavy isotopes. So we have the two options, fission and fusion. The advantage of using atomic energy is evident. The energy density packed in the fuel is incredibly much higher than from chemical reactions. Here just some examples. We start by burning wood and with the energy of 16 megajoules per kilogram, and Diesel is like 40 megajoules per kilogram, but nuclear fuels goes to millions of megajoules per kilogram. And fusion is even more efficient than fission by some factor 2 to 3 because of the graph that I just showed earlier. So really, one of the main advantages of fusion is the huge energy density in the fuel. That means it is practically an inexhaustible fuel and well distributed around the world. It's, of course, environmentally responsible, no greenhouse gas emissions, no long-lived radioactive waste, as the byproducts of a fusion reaction are light elements. It's inherent in safety and concentrating energy. So it's produced in a power plant, which has some advantage as regards the distributed energy, like most renewable energy. One element that I would like to emphasize again is that there are different reactions from nuclear fusion that can be used effectively to produce energy, but by far the most effective and the most promising is the reaction between deuterium-tritium. And this can be seen by the cross-section of reactivity between the different reactions in this graph as a function of temperature. And the relevant temperatures that we're talking about, you can see the blue curve, the efficiency or the reactivity of DT is much, much higher, at least one or even more than one order of magnitude than the two most competing ones, which deuterium-deuterium and deuterium-helium-3. I think this is important because it means that we have to live with, if we want to achieve fusion energy, we have to live with tritium because you need a fuel cycle. Tritium obviously does not, exist in nature, but in very small, minute quantities. So tritium has to be produced. This is produced through lithium. So there is a fuel cycle. There needs to be a production of tritium in the fusion plant that feeds the reaction with deuterium via the use of the 14 MeV neutron. And these two facts, that we have to have a fuel cycle of tritium and a very high energy neutron, has a very important impact in the development of fusion technology that I will further elaborate later. This is the reason, again, that the most developments of fusion energy focus on the deuterium-tritium reaction. This is a table of the emphasizing that the most private initiatives, like the public initiatives for the development of nuclear fusion, focus on the deuterium-tritium reaction, although not exclusively. This is a vast majority. So how do we do this? There are many ways. Obviously, the sun uses gravitational confinement. This is obviously working. Otherwise, we wouldn't have functioning stars. But gravitation is a very weak force, and you need a very large volume and the very low energy density of stars is not going to be translated in a practical application to energy on Earth. But we have stronger forces. In particular, we have magnetic confinement. That's what we use in EUROfusion. We're pursuing, but there are other options like the inertial confinement, which also EUROfusion has some small but important keep in touch activities. It's already been discussed in the context of Renaissance fusion. There are two main approaches to magnetic confinement: the tokamak, which is the main line of EUROfusion, but the stellarators have some definite advantages, and EUROfusion also has important research in the stellarator line. Fusion, as I said, fusion research is a worldwide effort. EUROfusion gathers the European effort. We integrate the fusion science and technology across all research laboratories in Europe. We have research across 29 countries with 31 research institutions, many more universities. We gather more than 800 students, and we have more than 4,000 fusion researchers and support staff across Europe. What is our role? Of course, as it was mentioned earlier in the context of Fusion for Energy presentation, EUROfusion assists the developments at ITER and it will play, hopefully, a very crucial role in the ITER operation and the scientific exploitation of ITER. We have a very important role in training and education, guaranteeing a workforce for future exploitation of ITER and other devices. And we are involved very strongly in the development of not only ITER, as I said, but next steps that were already mentioned today, like a demonstration reactor or a fusion power plant. We do that by coordinating an integrated demo design. And another important aspect that I must emphasize as well is that EUROfusion plays a very important role in ensuring the cohesion of the European fusion program. I already mentioned the strong support for ITER and the strong support for the next step device demo, addressing the technology R&D needs and gaps. This is done in parallel to the ITER program, and we maximize the lessons learned from ITER towards a next step device like demo. The way we organize our research is outlined in the Fusion roadmap. The roadmap is structured in terms of missions, and I highlight them here because this gives you a feeling or a view of the technologies and the physics that we need to address. We need a burning plasma, so most of our research in terms of physics goes into study and develop the best techniques to have this burning plasma in the fusion conditions. The heat exhaust from the plasma is a very important concern, so a lot of research goes into this area. We need neutron-resistant materials due to this very high energy neutron. We need an adequate fuel cycle with adequate tritium self-sufficiency. We need at the same time implement correctly and adequately all the intrinsic safety features of nuclear fusion in an integrated demo design, but not precluding the importance of having a competitive cost of electricity at the end of the day. And I'll come back to this later. And again, I emphasize, although our research is focused on the tokamak line, we see the stellarator as a very important option in the long-term future that we are still researching today very actively. So I think this is an important slide for this meeting, because these are the most important technology gaps that are still being addressed. And this covers a wide range of technologies. One important feature of fusion research is the spectrum of technologies that are covered are really vast. So this means that we cover all the technologies needed to breed the tritium through a breeding blanket concept, all the metallurgic, neutronics, fluids transport, all this integrating of all these technologies, all these analyses to be able to extract the heat from the plasma and from the neutrons, shielding the magnetic coils, at the same time breeding the tritium is one of our, or if not the key technology that still needs to be developed. So these are very important opportunities for industry to collaborate with the fusion research. We mentioned also today a very important aspect of materials, again, because we are handling the very high energy neutrons, and the IFMIC DONIS project is key to this respect. We need to develop adequate ways of extracting the power from the plasma through what we call the diverter. So The exhaust problem still requires advanced materials to protect the components from the extreme conditions from the plasma. We need to integrate the plasma scenarios, how we create the plasma, how we maintain the plasma, and how then we terminate the plasma through a very integrated control strategy. Again, opportunities to develop advanced controllers that are applied to different industrial applications, from fusion to industry, from industry to fusion. Again, safety is paramount. We need a clear safety strategy and waste management. Although the waste levels from fusion are of a different level that produced from fission, there is still a waste management issue to be handled. And last but not least, due to the highly activated materials that the fusion reactor has to handle in terms of the in-vessel and the components that are exposed directly to the neutrons, remote maintenance using robotics is key for fusion development. So again, very large opportunities for industry collaborations and partnerships. I will now conclude this presentation by emphasizing our EUROfusion technology transfer activities. I summarize here the aims and the objectives. What we want is start aligning our work practices with industrial standards, because the construction and operation of a demonstration and fusion power plant will be ultimately led by industry. Our designs need to take into account the requirements for eventual industrial production. We need a smooth transition from the development phase towards commercial use of fusion power. And we need to have an industry platform fully aware of all technical aspects related to fusion, so then the commercialization and use of fusion in a widespread environment has to be done as smoothly and as quickly as possible. The way we do it in EUROfusion is through a consortium of brokers. This acts as an interface between the fusion and non-fusion industry through a methodology and tools that have been developed and proved efficient. And the know-how of these technology brokers is needed to face challenges within the fusion market. So we put together a group of people that understand these challenges and help us linking the fusion development with non-fusion applications. At the moment, we have a consortium within a consortium, to put it this way. Our network of brokers are composed by 6 brokers or 6 organizations. To cover Spain and Portugal, we have Kim, that has been paramount in the organization of this event. So I thank them again for putting together such an efficiently and such a good event. But I mentioned also RINA, that covers Italy and Greece, CESAC and EURA, Germany, Austria, Verhart, Belgium and the Netherlands, and the lead broker, Innovation Extenso in France, but they also cover other countries like Finland, and they are exploring also collaborations and interaction with Sweden, Poland, Croatia, etc. But an Extenso Innovation Croissants, our prime, leads this network and acts as a main broker for France, as I said. We have a number of key performance indicators that drive this network in terms of technology transfers, the preparation of technology descriptions for a market push, also technology needs from the companies or from the industry through a market pool. They developed inputs for success stories and published success stories. This is very important for us because it's an important element of convincing our decision makers that fusion is already delivering a very important value to society already now, independently of the huge promise that we have for the future energy production. I emphasize that we do this closely with Fusion for Energy. We have completely integrated activities now. We have a joint EUROfusion and Fusion for Energy marketplace, and we have an integrated open call for demonstrator projects that I will describe in a little bit more detail in the next couple of slides. So these are projects or partnerships with specific applications that EUROfusion supports at the level of 50 kilo euro per project. And this acts as a small incentive of a prototype. If there is a technology that is being used for fusion that has potential application outside the fusion environment, we can put together some seed money or some seed funding to demonstrate further and further develop this promising application into something that then can be further developed towards an industrial application or marketing or new product. I give you some examples to give you first a good idea how wide range is the fusion field in terms of applications, but also some examples of success that we have done or we have had recently. Tungsten is a very important element for fusion because of its properties, and we have applied the tungsten alloys to extend the life of corona discharge electrodes. This was a project done together with Cedrion. We used our extensive fast camera array technology to detect fast events within the tokamak to monitoring the quality of fiber optic manufacturing. This is a project done together with Aprex Solutions. Regarding tungsten and tungsten fiber composites, we had a project in developing this kind of materials together with Brookman. Again, the fact that we use in fusion very high heat exhaust applications, we have developed together with the industrial partner SICOM protective coatings for combustion chambers for aerospace applications. We have a project together with Capteos for generating very intense electromagnetic fields using lasers. We had, we still have a collaboration with the Chromodynamics, which is a startup that uses methods developed to monitor the plasma exhaust in tokamaks through imaging to more accurately and in a cheaper and faster way analyze slices of tissues, of sample tissues of humans in cancer research. We developed together with ALMAG sensors to measure hydrogen in liquid metals. This is very important for manufacturing of alloys in industry, but also very important for fusion research in terms of the breeding of the tritium. And last but not least, we had a project very recently with Tomorrow's Motion to use advanced superconductors from Vision Electric to enhance these projects from Tomorrow's Motion in terms of magnetic propulsion using these advanced superconductors. I would like to conclude this brief presentation by, in terms of the impact of fusion towards the production of electricity or energy in general. This depends a lot in how fusion then is produced and what are the technologies and how mature the technology and when it becomes available. This is a very recent study that I took from a source from developer through in US with the MIT. Of course, the penetration of fusion in the market shown here in pink depends on how cost effective a fusion plant can be built. And the capital investment is a main driver of the cost of the overall process. And assuming the readiness for commercialization will come in 2050, then the penetration into the market depends strongly how cost effective the fusion energy will be at the end. This, of course, takes into account different assumptions. Our own studies is using the best knowledge we have is not so optimistic, but still optimistic that fusion by the end of this century could have a significant penetration in the market together with a strong use of renewables and a strong use of fission in a total decarbonized scenario for energy production beyond 2050. I come to some conclusions. I again focus on the fact that fusion development is a very long-term effort, but therefore it's very important to maximize the socio-economic impact of fusion activities by technology spin-offs to industry. So if you are involved in a project that could make use of fusion technologies or vice versa, you can please get in touch. We need to be very open-minded in terms of how the technology developed by fusion can be used in industry, but on the other way around as well, how industry developments can be used in contributing to further advanced realization of fusion energy. And I finish by thank you again for your attention and giving the contact of Fabio Vinagre, which is the contact person for industrial relations in EUROfusion, and our lead broker in Extenso Innovation Cross is organized through Nicholas Lower. So I leave here his email contact. If you would like to contact us, please do through these two email addresses. So thank you so much for your attention, and I'm happy to have any questions or discussions if it is appropriate.